Okay, so we're going to start this new unit, which is kinetics, which means rates of reaction, rates of chemical reactions and what they depend on, that sort of thing. It's really quite different. It's a bit more mathematical than other units we've been doing. So some of you might like that better. Some of you might not like that better. I mean, it's really, there's lots of things to choose from in Chem 104 when it comes to things to like and not like. So, all right, anyway, so we're done with solutions. Oh, by the way, I just realized, of course, we just finished Unit 3, that I never posted the Unit 3 homework, which is pretty stupid, but nobody reminded me either. So,
I was gonna ask today.
yeah, the Unit 3
Yeah.
homework is posted, but yeah, I also posted the Unit 4 homework. So I think what I'll do is I was going to drop one homework, but I'll drop 2 homeworks. So if you don't have time to do Unit 3, you know, you probably would benefit from it. Our exam is going to be after we finish Unit 4. But yeah, so let me write down, I just posted Unit 3 homework. My bad. I think most of the time students do the homework at the end of a unit, so maybe that's convenient for you. I could extend Unit 4. But anyway, if you decide not to do Unit 3, I'm going to drop 2 homeworks instead of 1. Okay, because I really screwed up on that. So we're going to start for Unit 4, which is called kinetics. And this is really about rates of chemical reactions. And I'm going to start by showing you a video. I usually do this demo in person, but obviously that's not happening this year. So I'm going to show you this video of a chemical reaction. It's between a very large molecule called crystal violet. And it has a beautiful color, as you will see. That's why it's called crystal violet. It's actually not a molecule, it's an ion. It's actually a positively charged ion, but it's very stable because it's just, it's really large and it stabilizes that positive charge. So it's a reaction between crystal violet and the hydroxide. What's the hydroxide ion? Anybody know what that is? What the formula is for hydroxide?
OH group.
OH minus. Good. All right. So it's, and then it just forms a product, which I'm going to show you. Actually, I should have a picture of the reaction. But the basic idea is that this is that purple color, right? And of course, hydroxide has no color, but the products are also colorless. So what happens over the course of this reaction is that you see the purple color fade. Okay. And as the purple color fades, you know that the reaction is happening. So the purple color is telling you how much crystal violet is there. And as it fades, it means the crystal violet is disappearing. It's reacting away and forming something that has no color. So I'm just going to show you these structures because they're so cute to look at, right? Look at this. It almost looks like a flower, you know? Well, not exactly. This is the positive charge here that I was telling you about. It's actually on a carbon, which you almost never see. That's called a carbo cation. And most of the time when one comes across a carbo cation, it's a short-lived species. It only lasts for a little while because it's unstable. But these are benzene rings. Each one of these rings is a carbon, well, 6 carbons. Okay, and each has a hydrogen. And every other bond is a double bond. So this is what one of these rings looks like. And you can see why it's not written in here, because it would just complicate the structure. So, and actually there are two resonance forms, so that the double bond is here or here. And so what we actually do is we draw a simplified notation of that just by putting a circle inside that hexagon, and that's a benzene ring. So these three benzene rings really stabilize this positive charge. If you were to calculate the formal charge on this carbon here, do you remember how to calculate formal charge? You count up half of the bonds that this carbon is involved in and all of the lone pairs, but there are no lone pairs. So it's just half of 3 bonds. So there's 2 electrons in a bond, half for each atom involved. So that's only 3 electrons. So 3 electrons are for carbon, but carbon has 4 electrons when it's just the valence electrons. So this is 1 fewer electron, which is why it has a +1 charge. Okay. Anyway, that's the interesting thing about this structure. The basic thing we're interested in is it goes from purple to colorless as this reaction goes on. So, so we abbreviate this reaction, as I told you, as CV plus OH minus goes to, and then basically what's happening here is you have this bond forms between the hydroxide and that carbon. Okay. And then, like I said, the purple color fades. So I'm going to show you this reaction in 2 flasks. So I'm not just going to run it once. I'm going to run it in 2 different Erlenmeyer flasks with 2 somewhat different concentrations. Okay, so what I will have in each of these flasks is I will have the same concentration of the crystal violet in both flasks. But I'm going to change the hydroxide concentration. I'm going to have, this is going to be 1 and this is going to be 2. I'm going to have twice as much hydroxide in 2 as in 1. Okay, so the concentration, and for this unit, we always use brackets to represent molarity. Okay, so the concentration of hydroxide in flask 2 is double what it is in 1. Okay, and we just want to take a look and see what happens to the rate of a reaction when you change or double the concentration of a reactant. So, okay, so let me go to that video. Exit full screen, that's what I have to do. All right. Oh yeah, I have to share my screen. Oh yeah, I'm getting it. I'm getting it. All right, so here I am. So on the left here, I'm going to explain this in the video, so I might as well just run it. So for this demo on the crystal violet hydroxide reaction, I have 2 500 milliliter Erlenmeyer flasks, as you could see, and they have in them each the same concentration of crystal violet, 40 milliliters of 3 × 10⁻⁵ molar crystal violet. And also I've added 60 milliliters of water to each one. So they have exactly the same things in them. And if you could read the signs there, that's exactly what it says. And next to each one, I have a little beaker. And on the left one, I have 10 milliliters of sodium hydroxide, 6 molar, pretty concentrated, but I've diluted it with 10 mils of water. While on the right side, I have 20 milliliters of sodium hydroxide. So 6 molar. So the flask on the flask number two, has twice as much, well, when I add the sodium hydroxide, it will have twice as much of that reactant. So we're going to see the effect of adding that, doubling one of the reactants as we watch this. So the one on the left has half the amount, the one on the right has twice, that amount. And I'm going to run this reaction by pouring those sodium hydroxide samples. I'm going to try to do it at exactly the same time. Just adjust this a little bit. So I'm going to pour one into one and one into the other. Get ready. And now I'm going to swirl them. And what its reaction is it's the color is going to fade. And we're going to see how fast it fades. Get this out of the way. So what do you see happening? So, I mean, it's not earth-shattering or anything, but you can clearly see that the flask on the right, or number two, is fading much more quickly than the number one, because I've added double the amount of the sodium hydroxide, and they each have the same amount of the crystal violet. So in this reaction, of course, the crystal violet is what's causing that purple or violet color, and the hydroxide that I add is bleaching out that color, is making it go away by causing a reaction to form a product that's not colored. So here we are now, and there's not too much color even on the left, but there's still a little. And no color at all, really, that I can see on the right. Okay, so this is about done. Okay, let me stop this. I don't know who this guy is. I'd really like to X out of this. All right. Okay. Here. Okay, now okay. All right. So I just want to go over what we can say, what we can learn from this experiment. So I have to go and hold on. All right. All right, so here we are, and I have another handout here, a handout about the demonstration of this reaction. So let me just move this up a little. So what did we see here? It says they have the same, so this is just telling you exactly what I've already told you. They have different concentrations of hydroxide ion, and it says that a disappearance of purple color indicates that crystal violet is reacting away, as I've said. What happens to the rate of this reaction when the concentration of hydroxide is doubled? Okay, so that's a very simple question. What's the answer to that simple question? I'll start to write for the flask where the OH minus is doubled. Hold on a minute. Can't do that. Am I sharing? I am, right?
Yes.
Okay, so for the flask where the hydroxide concentration is doubled, the rate, what happens to the rate?
It's faster, increase.
Is faster, right? Exactly. Very simple answer there. Okay. So what can we say about how the rate of a reaction depends on reactant concentration? So if we just generalize that, we would say, hold on, I gotta get someone else in here. We would say that reaction rate increases as the concentration of reactants increases. Oh, I don't know how to spell this. Increases. So greater concentrations of reactants means greater rate of reaction. But I'm going to use this reaction to sort of think about something that's a little harder than this. I'm going to move this up so you see that again. Hold on. Okay, so I want to think, this is sort of a more of a thought question, thinking question. Okay, so here's the question. We know reaction rate increases with concentration. At the beginning of a reaction, when you have all your reactants, okay, the concentration of reactants is greater than at the end. Right, that's pretty obvious. During a reaction, the reactants react, so they go away. So you have a lower concentration of reactants at the end of a reaction than you do at the beginning. So what does that tell you about the rate of a chemical reaction over the course of the reaction? So what do you think about that? Just take a minute to think about it. To me, this is so obvious, you know, but I've been doing this a long time. So what must happen to the rate of a reaction as it goes on? Because most reactions, so many reactions don't happen instantly. Even if they happen instantly, they don't happen all at once.
The rate has to slow down, or
Sorry, can you say? I just didn't hear you.
does it slow down, or
Exactly. Reactions slow down as they happen. The rate of a reaction starts out fast and as reactants get used up, it goes slower. Okay. All right. So I'm going to show you something else. I'm going to sort of prove this to you by showing you some other data. In the past, I used to do this in class, actually. But over time, well, actually, I even did it a couple of years ago. Yet last year we had the pandemic. I didn't do any of this, but anyway, I want to do a little more with this reaction. So I want to talk about how could you measure the rate of a reaction. What is the rate of a reaction? You know, when you think about it, the rate of a reaction is the change in concentration over the change in time. It's kind of like how a rate of speed, you know, the rate your car is going is the distance, the change in distance in a way over the change in time that passed. Now, this is very typical for things that are rates. So in order to measure the change in concentration over the change in time, I need to be able to measure concentration. Measuring time is easy. I can use a stopwatch, but I need to be able to measure concentration. And I need to be able to do it sort of continuously as time passes. Well, not maybe continuously, but at intervals. Okay, so one really good way to measure concentration of reactants is if they happen to absorb light. So, you know, we've used in the past this thing I've called Beer's law. And Beer's law says that the absorbance of a sample is proportional to the concentration of that sample. We used this in the copper lab week 2, I believe, when we did the concentration of copper, and we compared it to a known concentration of copper sample. And we used this proportionality between absorbance and concentration to figure out the concentration of the unknown. And then we use that to figure out the percentage of copper. So this is Beer's law, but if I put in, you know, when you have a proportion like this, it means that it's equal to a constant times the concentration, all right? That constant looks funny. It's 2 different constants actually, but it doesn't matter. It's constant, and we know what this number is. This is well known for crystal violet. Crystal violet is a dye, and we know a lot about its absorption of light. In fact, we know that these 2 together equal 40,000 in the funny unit inverse molar. So you multiply that by concentration and it gives you the absorbance. Or alternatively, we could take the measured absorbance. So we're going to measure absorbance as a function of time, as time passes, and divide that absorbance by this constant. And that will give us the concentration in molarity units. Okay, so what I've done in many classes in Chem 104 is I set up one of those little spectrophotometers like the one I showed you in the copper week 2 lab. I have students read out the absorbances at 10-second intervals. And what I'm actually going to show you are the results from looking at the crystal violet experiment. So it's this same CV hydroxide reaction using a spectrophotometer to get the absorbances. So what you're going to see is, okay, as the crystal violet reacts, its color is fading, but the chemical in there, the crystal violet, also absorbs light. And since it's going away, it's absorbing less and less light as time passes. So here is a set of data for crystal violet as a function of time. I don't know why I'm so concerned with not having gaps. It's stupid. But anyway, what you can see here, if I sort of blow it up a little bit, okay, you could see that I took data, or the students and I took data every 10 seconds. Now, by the way, what I did was, the experiment we looked at, it was sort of all over in 20 seconds. So what I did with this experiment was I used lower concentrations of the hydroxide and the crystal violet to slow down the reaction, because I know that if the concentrations are lower, the reaction rate will be slower. It'll go slower. All right. So here you can see I have data for every 10 seconds. And this is the absorbance here. And I start out with high absorbances, 1.86 at the beginning of the experiment. By the end, I'm down to 0.16. And the other thing I did, besides plotting it, which I'm going to show you in a minute, was on Excel, I took the absorbance. Remember, A equals 40,000. That's that EB constant, doesn't matter, times the concentration. That what I did to get this column was I took the absorbance and I divided each one by 40,000. That's how I got from here to here. So these guys here are the concentration of the crystal violet as the reaction progresses. And these go down because the concentration of reactants is declining with time, decreasing. Okay, so we start out at 10 to the minus 5th molar, we end up at 10 to the minus 6 molar. Okay, so what I did then was I took and made a graph. And I just want to show you here, on the y-axis, I have the concentration of the crystal violet, right? That's what's in this column here. And on the x-axis, I simply have time in seconds. Okay, so let's just look at a couple of these points because I just want to prove to you that this is indeed what I did. So here I have, this is the first point at 0 time. And when I started taking data, it was 4.13 times 10 to the minus 5th molar. Okay, so you can see over here, if you blow up the graph, that's what this number corresponds to, right? That's 4.13 times 10 to the minus 5th molar. And then let's look at the 10-second point. That's right here. That looks like it's between 3 and 3.5 times 10 to the minus 5th. Okay, yeah, 3.29 times 10 to the minus 5th. So what this graph is showing you here is just a plot of how the crystal violet concentration changes with time. And what I want to show you is I took and made a line here. I sort of draw a line that's like tangent to the curve. That's telling you kind of what the slope of the curve is here. Now, this is a curve. This is not a line, this blue line. This blue curve is not linear, all right? But what I did was I put a line sort of up against that curve at the beginning of the reaction. And I did the same at the end of the reaction. And what you can see, if I figured out this I would call the initial slope. All right, if we had a linear graph, then the initial slope and the final slope would be precisely the same because that line has a single slope. But this is a curve. This is a curve that's showing the change in concentration with time. And the initial slope, well, how do you calculate a slope, right? It's the delta y over the delta x. So delta y over delta x, which is the change in the concentration of the crystal violet over the change in time. Okay, and you could see that it's got a very steep slope. Now, what is that slope equal to? Look what I just wrote here. I wrote, this is the change in the concentration over the change in time. That is the reaction rate. If you go back, you see, I think I told you that at one point. Maybe I didn't, but but anyway, I'm telling you now, a reaction rate is a change in concentration divided by a change in time. This delta means change in concentration over change in time. So we just write it as delta concentration over delta T. Okay. So I could also write it as, well, so what you see here is at the beginning of the reaction, you have a steep slope, which means you have a large rate, because I said the rate is that slope, basically. At the end of the reaction, if I pick this, the end of the reaction, now, if you look at the delta y and the delta x, which is still the change in concentration over the change in time, it's much shallower. It's much less steep. So this means it is a slower, a smaller rate. Okay, does that make sense to you? Just yeah, good. All right. I saw one person nod her head. Thank you very much. So what this illustrates, not besides the fact that it tells you that you can get the rate, well, you can get the initial rate, right, of a reaction by measuring how the reaction's concentration changes over time at the beginning of a reaction. And you could see that the reaction rate continuously changes as reactions occur. And the reason why that is of course, because the reactants are reacting away. So when I talk about the reaction rate, you know, well, there isn't any the reaction rate. That reaction rate is changing every second that the reaction goes on. So most of the time, this means the initial rate. Okay, and you'll see some problems that we do later on in class today, where one of the columns in the data is called initial rate. And you should be thinking about this graph and thinking about the line that represents the initial slope of the of that graph of concentration over time. Okay, there is a detail that maybe some of you picked up that I left out that I have to go over now. I wish I could just leave out all the details that are a pain in the butt, but I can't really do that, you know. So the detail that I left out had to do with the sign of that slope. Okay, so if we go back and look at this graph, this line here has a negative slope, and I just sort of totally glossed over that. So this has a large negative slope. This is a smaller negative slope. Okay, so why is that slope negative? Does that mean the rate of reaction is negative? No, that's not what it means. Rates of reaction we always think of as positive. But so what's the deal? So why is the slope negative? The slope is negative. And the reason why it's negative is because crystal violet is a reactant. And so as a reactant, its concentration is going down. So if we take the change in concentration, well, the final minus initial, okay, we take the concentration here and the concentration here, we subtract, you know, we take this minus this, it's going to be a negative number. And that's simply because the concentration is going down. Okay, so we always change the sign when we're talking about a reactant that is disappearing. So that's how we solve the whole thing. We always change the sign of the delta concentration over delta T to make it positive. And you could think about it for a reactant as being the rate of loss of a reactant. So here, the rate is actually the negative of the change in the crystal violet concentration. So this bracket here is simply the concentration of CV plus. Okay, so I'm just writing it in that notation that we're going to be using over delta T. This is the same as the change in the hydroxide ion concentration over time. This is also a reactant. I also need to put a negative sign in front of it. But if I wrote this, because as these, everything is 1 to 1 to 1 here. We have CV plus OH goes to products. And we have, basically 1, 1, and 1. So every time you lose a CV, you're losing a hydroxide. Every time you gain a product, you lost one of these and one of these. If we wrote this in terms of the change in the product concentration over the change in time, do I have to put a negative sign there? What's happening to the product as this reaction is going on? Is it going down or up? You're forming products, right? So product concentrations are increasing. So I don't have to do anything. This is already positive. Why is it already positive? It's because products are forming. Their concentration is increasing. So we don't have to worry about those silly difficulties, all right? Okay. So I said that reaction rates depend on concentrations of reactants. So I said this, right? But often it's not obvious exactly how the rate depends on reactant concentration. So it's not always obvious exactly how rate depends on concentration. And that becomes our first job here, is to figure out how does a certain reaction, how does its rate depend on concentration? So we try to do this, figuring out how a rate depends on the concentrations of its reactants. We call this something. We call this finding the rate law. Okay, so the next thing we're going to look at is how do you find a rate law? First of all, what is a rate law? Okay, so that's the first thing I'd like to talk about, right? So what is a rate law? Okay, well, a rate law, let's take the hypothetical reaction. A plus B goes to product. Question? Someone's got a mic on. Oops. Not very good at this, All right, anyway. So if this is sort of a hypothetical reaction, what we want to do is we want to figure out how does the rate depend on the concentration of A and B. So that's what this means, the concentration of A and the concentration of B. So it's going to be equal to some constant times the concentration of A, but not necessarily to the 1 power, right? Right here, we just have concentration of A. That's the same as A to the 1. In fact, it could be raised to a small power like 0, 1, or 2, or even 3. So And the same is true for the B. So what I'm saying here is that the rate is going to be proportional to the concentration of each reactant raised to a small whole number power. So these are small whole numbers. And these numbers, M and N, can be, it can be 0, it could be not depend at all. I'll talk to you more about that. They can be 1, they can be 2, and in rare cases, even 3. So it's our job to figure out the rate law. And determining these values of N and M. So finding these numbers, finding the N and the M for a particular reaction, not the hypothetical reaction, is called finding the rate law. And then you'd be able to write this expression. And this rate, by the way, if I just for a minute go back to what we were learning just before this, okay, this rate is equal to the change in the concentration of product over the change in time. And how would I write it in terms of the change in A over the change in time? What would I have to put in here to make it complete? Are these two equal? I mean, it's a little bit of a tricky, silly question. I mean, as this reaction happens, A goes away and product forms, and they form with exactly the same rates. However, A is going away and products are coming in. So they are the negatives of each other. Okay, so this is another way I could write the rate. I could find the rate by measuring, say, the change in the concentration of B with time. And the negative of that would be how the product would change with time. We want to figure out, what does that equal? How does this depend on the concentration of each reactant? Is it going to be raised to the power 1, the power 2? These are the possibilities. So determining these little numbers here is finding the rate law. Okay, so I'm going to go over a few possibilities that this could be and try to get us a little bit more familiar with this. All right, so what are the possibilities? I'm going to go over some of them, not all of them. Okay, so suppose we find out that the rate is proportional to A to the 1 power and B to the 1 power. Okay, so I wouldn't write this with the ones, right? Because A to the 1 is just A. I would write it like this. If that's the case, then I would say that the rate is first order, because this is a 1, in A, and first order in B. Okay. Another possibility, so this is possibility number 1. Another possibility is if, let's say, the rate, and I'm talking about like that initial slope of that reaction, okay? Is it proportional? Is it equal to K? By the way, this K is called a rate constant. We'll talk a lot more about that later. Later on in the unit. It could be K A to the 0, B to the 1. Okay, A to the 0, well, that's just 1, right? So I wouldn't even put that there. I would write that this way. Okay, then I would say that the reaction is 0th order in A and first order in B. Okay. What about if I had this? If that was the case, that would be the same as writing Ka squared. This would be 0th order in B, 2nd order in A. Okay, and if it's 0th order in something, a lot of times we don't even bother saying it. It's just not there, so we don't even mention it. So I'd say, okay, the reaction is 2nd order. And so there's all these different possibilities that can be the case for a particular reaction. So how can I figure out the rate law? Okay. So the way to do this, if you're, you know, in the lab, right, in the lab, what you would do is you have to have some information. So you need info on how the rate of a reaction changes when you change the concentration of reactants. And to do this, you would really need to change one reactant's concentration at a time. That's a controlled experiment. If you change both, you won't know whether changing one or the other was the one that affected the rate in the way that it did. So you must change the concentration of just one of the reactants at a time. Okay, so so I'm just going to sort of go over some basic, almost math with you. I'm going to call it basic math. So I'm going to consider what would happen if you have a first order reaction, first order in A. So suppose a reaction with A as a reactant is first order in A. Okay, so rate is equal to Ka to the 1 power, or just Ka. K times the concentration of A. Now, this means that the rate is simply proportional, right, to the concentration of A. Taking that a step further, we know what a proportionality means. Well, in fact, you could write, you know, rate equals Ka is the other way of writing it. But when you have a proportion like this, it means that whatever happens to A, whatever change you make to A, you're going to have the same change in the rate. So that's what it means. Whatever happens to A, the same thing happens to the rate. Okay, so for example, if I double the concentration of A that I start out with, okay, if I double the concentration, what's going to happen to the rate? The rate doubles. Okay, you could see that here. If I suddenly multiplied that concentration of A by 2, it would end up multiplying the rate by 2 because they're proportional to each other. Let me give you a very simple example. If I tripled the concentration of A, the rate would triple. But usually in this class, we focus on what happens when you double the concentration of a reactant. So I'm going to, let's give you an example. So suppose the concentration of A is 5 molar, right? That just means molar concentration units. And then, so my rate which is a constant times the concentration of A, if I put in 5 for that, I end up with 5K, right? This is 5. I plug in the 5 here. So that's what my rate is going to be. But now, if I double the concentration of A, so I make it 10 molar, okay? So what is the rate then? It's K times 10, or 10K. It's like a race. So you could see that here the rate was 5K. Now the rate is 10K. So the rate also doubled. That's what it means to be a proportion. Okay, but now let's do the next level up. All right. What if the reaction is second order in A? All right. So that means the rate is K times the square of A. And suppose again that, so what if the concentration of A is 5 molar again, right? But now what is the rate? What's the rate equal to in that case? K times what?
20.
I just didn't hear you. 5 squared, right? Because there's a 2 here. 25K. That's the rate. This is a different reaction, right? It's a second order reaction. So now, if you double the concentration of A to 10 molar, what is the rate? K times, what do I put here? K, A squared. A is 10 squared. What does that come out to? What's 10 squared? Oh, sorry, I'm not even reading the chats. 100K, exactly. All right, good. So I went from 25K to 100K. That is not a factor of 2. That's a factor of 4. So when you have a reaction that's second order with respect to a reactant, and you double that reactant, it quadruples the rate. Okay, so for a reaction that's second order in a reactant, doubling the concentration of that reactant doubles the rate. And, you know, if you're mathematically inclined, you could kind of see it like this. Here, the original rate is K A squared. Okay, let's call this concentration of A, the initial, let's call that A0, K A0 squared. Now double the concentration of A. So now it's 2A0. So the rate now becomes K times 2A0 squared. Well, but now I got a 2 in here. This is K times 4 times A0 squared. It's because of that square that this becomes a quadrupling, because when you rearrange this, you see it's 4 times what you had initially, right? This is the original rate, and this is what it becomes. Okay, so you have to keep that in mind when we do these examples. So for a first order, if it's first order in A, doubling A doubles the rate. If its reaction is second order in A, doubling A quadruples the rate. And then if you have 0th order in A, well, it doesn't depend on A, right? So doubling A doesn't affect the rate. So if you keep this in mind, while we do these problems, I think it will be great. Okay. So does anybody have a question about this? Want me to go over something? It's a good time to ask. I don't see anybody sharing their video now. I could use a little help here. It would honestly be good if a few people could. Come on. Thank you, Kara and Brittany. All right, Morgan, good, got a few, thank you. I don't feel like I'm talking to my computer screen. Okay, so I'm gonna go and do activity. We're gonna look at activity 2 of this new set of activities for unit 3. Here it is, activity 2. And I'm going to skip A for now. That's another detail that I have to go over with you at some point, and I'll get to it later. But I'm just going to recopy the reaction here, 2NO, because I'm not going to do A right now, plus Br2. So it's a reaction with a gas and liquid bromine to produce gaseous NOBr. Okay, so we have this reaction here with this stoichiometry, which we don't care about right now. This is what we care about right here. Okay, so what this is telling you that somebody went into the lab and did 3 different experiments with different concentrations of the 2 reactants. Here they're both the same at 0.1. Here one is 0.2 and one is 0.1. Here, the first one is 0.1, the second one is 0.2 molar, right? Because that's what those brackets mean. And then somebody measured, let's say they measured actually might be easy to measure the concentration of bromine because it's a brown color over time, and maybe made a graph and found that initial slope, which is the initial rate. Okay, there's a lot of work that goes into these silly little grids with little numbers, okay? But somebody had to find this out initially. Okay, so what it shows is the results of 3 different experiments with 3 different sets of initial concentrations of reactants. And what we need to do is we need to take one of them and then find the data for another one where one of the reactants concentration is doubled and the other one stays the same. With this set of data, I think it's pretty easy to do that. We only have 3 experiments. It's pretty clear that if we go from 1 to 2, okay? So if we go from, let's try, we're going to go from experiment 1 to experiment 2. And you could see that what's happening here is the concentration of NO doubles. So I'm going to write times 2 to indicate that it's doubled. The other thing that's very important, and students forget this all the time, is they have to make sure that with the 2 experiments that they picked, the other reactant stays the same. Like I can't pick 1N, well, here there's nothing that I can't pick because it's a pretty simple set of data. All right, so this doubles, this stays the same. And what happens to the rate? This is the rate here. What happens when you go from 12 to 48? What is that a factor of?
4.
It's a factor of 4, exactly. So we're going from experiment 1 to experiment 2. This multiplies by 4. So given what we just talked about, what does this mean? If so, I want to find the rate. Let me write down what I want to find. I want to find these 2 powers. Okay. Do I know something? From going from experiment 1 to 2, I double the concentration of NO and the rate quadruples, which means is multiplied by 4. So what is the conclusion here? So the reaction is what order in NO? What do I put in there? A doubling. A
Is
doubling.
that the second order?
Second order, exactly. Okay, so second order in NO. Okay. So now I'm going to go on to the next one, back to that set of data. Okay. So I've already figured out what happens when the concentration of NO doubles. Let's figure out what happens when the concentration of bromine doubles. So here, between experiment 1 to experiment 3, the Br2 doubles. Okay, this is times 2. And you have to check that this concentration stays the same. And now look at what happens to the rate. What happens to the rate? It doubles. So here, bromine doubled, the rate doubled. So what is the conclusion?
Is that the first?
First order in Br2. Okay. Whoever was it wrote NO is in the second order. Yeah, I mean, you were right. It was what you would say, though, is that the reaction is second order in N. That's the right way to express that. So we have that, we know that it's second order in NO and first order in Br2. And just adding those two numbers together, we say it's third order overall. So we just add M and N up together. Okay. Okay, so now the next part of the problem is, how do we find the rate constant? What is the rate constant for this reaction? Okay, so how do we get the rate constant? And I didn't really say anything about the rate constant, but the rate constants are extremely important. It's really all because of the rate constant, whether the reaction is going to be a fast reaction or a slow reaction. And the rate constant depends on different factors that we're going to learn about a bit later on in the unit. And one of the things it depends on is whether there is a large energy requirement for this reaction, what we call an activation energy. So reactions can be extremely fast or extremely slow, which means that this rate constant can be giant. It could be 10 to the 9th, or it could be 10 to the -8th. It really is a huge variation. So a very important thing is figuring out the rate constant, because this really tells you how fast the reaction is going to be. So we have the rate law, right? We know the rate is K times NO squared, right? Times Br2 to the 1, which I don't have to even put the 1 there, because we know it's second order in NO, so we know this number is 2, and first order in Br2, so we know this power is 1, okay? So we have this rate law. What we can do is go back to the data. Okay, so I'm going to go back up to the data here, and I'm going to pick one set of data. Oftentimes I just pick the first one. Oh, what's that there? I pick experiment 1. And experiment 1 is 10th molar in each of the reactants and has an initial rate of 12. So let me write that down. 0.10 molar NO, 0.10 molar Br2, and the rate was 12. And notice the units of the rate are always the same. Molarity per second. It's concentration over time. Rates always have those units. So what I want to do is I have this expression here, right, is K times NO times BR2, sorry, NO squared times BR2. And I want to find out what is the K. So what I do is I isolate the K mathematically. Okay. So I would basically take this equation and I would divide both sides by NO squared and BR2. So that these cancel out. Now I know most of you won't do that. You'll just plug in the numbers, but so be it. I can't change you. But anyway, so then all I would have to do is that now that I know that K is the rate over these concentrations, I just plug them in, right? The rate is 12, plug that in on top. NO is 0.10 squared. BR2 is 0.10. So, you might want to take your calculator out and do this calculation, because some of you will get it wrong because you don't know how to use your calculator properly. I just know it. I see it every single year. So if I were you, I would take out your calculator and do this calculation and see if you get 1.2 times 10 to the 4th, which is the same as 12000. Okay. Some of you are not going to get that number. And if you don't, you should stay till the end of class and ask me to help you with your calculator. Okay. Okay. So, all right, that's very nice. But in this class, you can't give me an answer without giving me its units. So we have to deal with the units, and the units are a little bit of a pain in the neck. What are the units of K? And the units of K actually depend on the overall order of the reaction. So let me just show you what the units are here. So what I'm going to do is I'm going to go back and say, okay, what's the units of the rate here on top? Units of rate is always concentration over time. And the units of concentration of NO, that's molarity, but there's a square. And here we have molarity without a square. So what I really have is molar per second divided by molar cubed, which I would write as molar per second times 1 over molar cubed. And you could see that one of these is going to cancel out. Okay, so we'll end up with 1 over molar squared seconds, which is usually expressed as molar to the -2, seconds to the -1. And this is the units of K for a third order reaction. It's third order because it's second order in NO and first order in Br2. Okay. So the way you would express the answer is 1.2 times 10 to the 4th. Because notice I put a decimal point here. That was actually wrong because that implies that all these are significant. We only have 2 sig figs here everywhere. So we only have 2 sig figs in the answer. So it's 1.2 times 10 to the 4th. Molar to the -2, seconds to the -1. So it's always going to be that same funny combination of units for a third order reaction. So you don't have to go through this derivation. You just need to remember or write down somewhere that this are the units for a third order reaction. Okay. I'm going to do another example. This is activity 4. And the reason I picked this example to do is because it's a little bit harder to find the data that you need in this one, because there's more choices of numbers. So maybe it's not so obvious. So the first thing we're going to do here is to figure out what is the rate law. So remember, we're trying to find those powers. So we know it's going to be the reactant. We have NH3 ammonia to the M, BF3 to the N. Okay, this is an interesting reaction. Okay. So what am I going to do? I have to look at my experiments. I have to look at all these, right? I'm going to look at them. And I'm going to find 2 where one reactant doubles, let's say, and the other one stays the same. So somebody tell me in the chat, what 2 can I pick out? What 2 should I look at? One and 5, excellent. Here's 1 and here's 5. So this is doubling. Concentration of BF3 doubles. So we go from experiment 1 to experiment 5. Concentration BF3 doubles. And what's happening to the NH3? Nothing. Nada. Okay. So what's now happening to the rate? What happens to the rate?
Double.
That's right. The rate doubles. So you could take the final one and divide it by the initial one. It might not always be so obvious. Sometimes there's exponents that change and you need to do that. But, you need to figure it out one way or the other. The rate doubles. Okay, so that means, what's the conclusion? Let's just start it. The reaction is what order in BF3? What's the answer there? First, exactly. What happens to BF3 happens to the rate. Okay, so let's look at the next one. What is another experiment from going from what experiment to what experiment does the N, we want the NH3 to double.
2 to 1.
2 to 1. I think you said that, right? Yes, exactly. 2 to 1. So it doesn't always have to be going down, you think outside the box here. Here we have the same. And here we have a doubling. And what happens here to the rate?
It doubles.
Doubles. All right, times 2. So we doubled the NH3. The BF3 is the same. And the rate doubles. This is actually very common. The conclusion is that the reaction is first order in NH3 as well. So this reaction, there's 2 reactants, right? NH3 and BF3. And in fact, it kind of looks like this. You have that ammonia with a lone pair of electrons and those 3 hydrogens. And then you've got this BF3, which is planar. It's in a plane. And boron, if you calculate the formal charge here, Well, the formal charge I think is actually 0. But if you calculate the electronegativity difference, you will notice there's a delta positive and delta negatives on each of the fluorines. So you have an attraction here between this electrons in that lone pair, and also you have a delta negative here on the nitrogen. And so these are attracted, and so you end up with a bond forming. And that's the product. It's written down over here, F3B NH3. And this is the bond that forms, okay? So fill in the following. The reaction is first order in BF3. It's first order in ammonia and second order overall, okay? And now we are going to find the rate constant. How do we find the rate constant? Well, you can go back and you could take data from any one of those experiments. I usually pick the easiest one. Like if they have one set of data where they're all the same concentration, I'll certainly pick that one. And I'm going to pick experiment 1 again because it is. So I'm going to pick experiment 1. The rate is equal to K times NH3 to the 1. So I'm not going to bother putting the 1 there, times BF3. I would isolate the K by dividing by those concentrations before I proceed. Old habits die hard, and I think my way is better. So I'm using it, even though most students would not do this. I never could understand why. All right, so I didn't look up the rate for experiment 1. The rate is 0.2130 divided by 0.250 and 0.250. Okay, so that comes out to 3.41. Okay, what about the units? Well, the units of the rate on top is molar per second. It always is. And then I've got a molar times molar in the denominator. So I've got molar per second over molar squared. That's molar per second times 1 over molar squared. One of these cancels, and you end up with 1 over molar seconds, which we often write as molar to the -1 seconds per -1. I often say per molar per second. The per is like means it's in the denominator, like miles per hour. The hour is in the denominator. Anyway, so I often say it like this. So the answer would actually, the full answer would be 3.41 per molar per second, or 1 over molar, 1 over second. Okay. I just want to go back to activity 2 because I skipped something, another one of those details that I want to go over before we finish today. And I have another activity after that if there's time, which I will have you folks work on. So, so we've been writing at the beginning of class, we wrote these rate expressions, you know, change in concentration over change in time. And this one is a little bit different because we have coefficients that are not all ones, okay? And so here the stoichiometric coefficients are not all 1. And that leads to a somewhat of a different, having to handle this rate ratio, this change in concentration over time a little bit differently. So this here has a 1. So the rate can be written as the negative because it's a reactant, remember. The reactants always get a negative sign in front of them. Change in BR2 concentration over time. Could I write this? Could I write at the rate equals the negative of the change in NO concentration over time? Could I write that? Would that be correct? If it's equal to this, can it equal this? And you have to think about these coefficients here. Is this the same? Does the NO concentration, let me write this down. Does the concentration of NO decrease, because putting this here is like the rate of decrease, at the same rate as the concentration of Br2?
No.
Was that a yes or a no? No.
No.
Somebody said no. Yes, the answer is no. If it wasn't no, I wouldn't be, even telling you about this. But the reason why it's no is because 2 NOs react with every 1 bromine. So that means you're losing NO at twice the rate that you're losing the bromine. So they're not equal to each other. You would have to take this rate here and divide it by 2. So multiply it by a half, okay? So I put a half in front of here. And now this is equal to the change in the Br2 concentration over the change in time. I have to put this here because NO is reacted away at twice the rate that Br2 reacts. Okay, so I have to put that there. So what you do is when you write this rate ratio in terms of reactants, okay, so when you write it in terms of reactants, you have to put a negative sign in front and you have to put the stoichiometric coefficient on the bottom. Obviously, if it's 1, it doesn't change it. Okay, so so for this reaction, and what is the reaction? Let me write it down again because I can't see it anymore. We have 2NO plus Br2 goes to 2NOBr. Okay, the rate is the change, the negative of the change in Br2 concentration over the change in time. It's minus 1/2 the change in NO concentration over the change in time because of that 2 there. And what about the change in concentration of NOBr over the change in time? Notice I do not put a negative sign here because this is forming. So to make it positive, I just leave it alone. I put these negatives here because these concentrations are both going down and I want to make the rate positive. So what would I have to put in front here? Right, this NOBr is forming at twice the rate that the bromine is going away. So I have to what? I have to put a 1/2 in front of it. Okay, so for reactants, in this change in concentration over change in time ratio, which is the rate. So I'm not talking about the rate law now. This is really a different thing. This is how you would measure it. Okay. For reactants, you would put a negative sign in front of this expression, and you would divide by the stoichiometric coefficient. For products, in the same expression, you would not no negative sign, It's already positive.
Professor,
But you would, sorry?
I just had a question. So for BR2, you wouldn't like do the 1/2 or anything for it? You would
No, because there's a coefficient of 1 here. So the reason why we put this half here is to put these on equal footing, is to make these equal the same rate, right? We can't like have a rate of reaction defined one way if we're talking about one reactant and another way if we're talking about another. And these, if I didn't put the half here, these, the delta BR2 over delta T, delta NO over delta T will be different numbers because NO with this 2 here, 2 of these react with every one of these. So that means that every time you're losing a bromine, you're losing 2 NOs. So that's disappearing twice as fast. So we have to put those loss of those reactants on equal footing. And we do that by dividing by the stoichiometric coefficient. And because bromine has a stoichiometric coefficient of 1, you don't have to do it for bromine. Do you get that better now?
Yes, I understand, but I have another question now.
All right, let me just write it down.
If
Yeah,
it
go
was
ahead.
a ratio of like 3:2, would you do something similar?
Well, there wouldn't be that because it's only, remember that delta T doesn't have anything in front of it. It's just, oh, and we always pretty much have, we always have whole number coefficients. So you're never gonna, well, that's not really true. In the last unit, sometimes we talk about fractional coefficients, but not when we do rates. These are always whole numbers, so don't worry about that.
Okay, thank you.
All right. Good. All right. So I have one more activity, and I would like you guys to do it because it's really easy to watch me do it, but it's not maybe so easy to do it yourself. So this is activity 3. And what I would like you to do is find the rate law. Oh, I can't get it to stop. So this is basically the what you need for the, oh, so there are two, the first, I don't know, this is C, this is A, this is B. The next one says, you know, I'm just going to move this up. And to find the rate constant. So all of this is part of this problem. So these are examples like what we've been doing. And I think what I'm, let's see, it's 3:31, so we have 20 more minutes. Do you think you should go into some breakout rooms? You want to put yourself in breakout rooms? What do you want to do? Or should I just assign them?
Can we just work like here?
You could do that if you want, but sometimes people like them. So I think I'm going to open a few up and people can go in if they want. All right.
Okay.
And if you want to stay, you can stay because there's 20 more minutes. And I think we'll reconvene at 3:45 and I'll go over this problem. All right. So I'm just going to open some up, but you could go in on your own. I'm going to open up a bunch of rooms. That's all. Or you could stay where you are. Okay. Actually, in the rooms, maybe you can't see this. Oh, yeah, that's a disadvantage, unless you copied it before class. Oh, yeah, this is posted, actually. It's posted on Blackboard under activity sheets, so you could get it from there as well. I ordered a fan for my computer. It's so hot now. It's incredibly hot. Anybody got a question? Okay. Hmm. Morgan, I have one comment though. It wouldn't be from trial 1 to 3 that you can conclude that it was from, that would be from trial 4 to 3 that you could conclude that, because NO is constant in 1 to 3.
Oh, okay.